Okay, now we're going to introduce some more operations that we can perform on matrices. And the first one that we're going to talk about is the matrix transpose. So I want to start with some examples, actually. So let's say we have a matrix A. Let's let this be a 3 by 3 matrix, and I'll just give it the entries 1, 2, 3, 4, 5, 6, 7, 8, 9. And now what I'm going to do is I'm going to construct a new matrix from this matrix A. And what I'm going to do is I'm going to get the following matrix. I'm going to get 1, 4, 7, 2, 5, 8, 3, 6, 9. And now you can ask, like, what happened here? What did I do? What I did was I took what we will learn is the transpose of a matrix. So this is referred to as the transpose of A. And what I did, if you'll notice, for a square matrix here, this matrix is square, you can see what I did is I've taken the rows and I've exchanged them for the columns. And I wanted to start with this example so we kind of have some intuition about what the transpose is doing. If you'll notice, I start with the first column, 1, 4, 7, and in the transpose, that becomes the first row, right? And so this is kind of what the operation is doing here. So similarly, like the second row here, or the second column was 2, 5, 8. 2, 5, 8 would be the second row of the transpose. And then same for the third row. Now, another way you can kind of picture this, which I'll bring up for those of you that maybe this way of viewing it helps with understanding. So kind of the main way we think about the transpose is swapping the rows and the columns, right? You have a matrix A, you change the rows for the columns, and then that new matrix is the transpose of A. Another thing you can think about doing is take the diagonal here. So here we have the diagonal of 1, 5, 9, and then mirror everything along the diagonal. And so what we did was we exchanged the 4 and the 2, right? Like if you use the diagonal almost as like a line of symmetry or something, then you swap the two entries that are in the symmetric spot, right? So you have like 4 would swap with 2, 7 would swap with 3, and 8 would swap with 6. And that's exactly what happened here, right? When we look, the diagonal stayed the same because that was our line of symmetry. And then 2 swapped with 4, 3 swapped with 7, and then 6 swapped with 8. This is another way you can think about what the transpose is doing if you would like. The problem with thinking about it this way is that becomes less clear when you're working with non-square matrices, right? So if you were to work with a non-square matrix, let's say I have the matrix B, which is 1, 4, 3, 1, 2, 6. Well, now if we think the transpose, if we think of the transpose as just being, well, we swap the rows for the columns, well, then we're immediately going to get like 1, 4, 3, 1, 2, 6, right? We can compute the transpose very quickly by just saying that we're swapping rows for columns. Let's try to think about this in terms of the diagonal argument here. Well, the diagonal argument here is what we have is the diagonal is just those two entries for the 1, right? Because that would be like the A11 entry and the A22 entry. The diagonal is always the AII entries. Maybe I'll write that. So the diagonal is always the AII entries. Okay. And now to see what kind of mirroring would look like, well, we still have that the 3 and the 4 would flip. We get that mirror here, right? But then the 6 doesn't really reflect across the diagonal, but it still gets kind of like there's no entry for it to reflect to, but geometrically, that line of symmetry still exists, right? And so it's a little less clear to think about this for the transpose in terms of when you have something that's not square. Again, geometrically, right, or just visually, you can still see the transpose doing this, right? Because when I reflect the 6 along this diagonal line of symmetry here, well, then it would appear over here. And same with the 2, right? The 2 that was down there would flip across this line and it would appear all the way up here like this. And so you can kind of see this for non-square matrices as well. But I think in general, how to think about the transpose and how to calculate it as quickly as possible. The best way of going about this may be to just remember that what we're doing is we're swapping rows for columns, right? So the first column of A becomes the first row of A transpose, and then the first row of A becomes the first column of A transpose. And so that's kind of what we're thinking about. We can write this formally in a definition here as the, so if A, let's let A be an M by N matrix, then we'll say the transpose of A is the N by M matrix given by, and let me come up here really quickly and say that we'll write A as the matrix with entries Aij. This was M by N matrix. Then the transpose is simply written as A transpose, and this is Aj. And you can see here, you're really just switching rows for columns. You can also see that the diagonal is remaining unchanged because the diagonal is when I and J are the same, right? So the diagonal never changes on the transpose because when I equals J, if you flip them, well, it's still the same entry. Okay. So we've seen now what the transpose is, and we even started with some examples. And so you'll want to do some more examples of computing the transpose of a matrix. But we do have a few properties here of the transpose. The first one is that if you have a matrix A and then you compute its transpose, but then you compute the transpose of the transpose, you get back to the original matrix. And this makes sense, right? You could prove this almost immediately because if A transpose is Aj, well then A transpose would go back to Aij, but that's just A, right? You could almost see this proof in one line there in red. We also have a rule with products. So if you have the product of two matrices, A, B, and then you want to take the transpose of this product, well, what you can first do is take the transpose of B and then multiply by the transpose of A. And notice the order here. The order is important because remember, matrix multiplication is not commutative. We also have a linearity property with the transpose, and that says if we have, say, a scalar R times the matrix A plus a scalar S times the matrix B, and we're taking the transpose of this entire term here, well, then what this simplifies to is R times A transpose plus S times B transpose here. And so these are some important properties when trying to, if you have like a complicated matrix and you could split it up into maybe a linear combination of simpler matrices, well, then computing the transpose would be easier in this way. I want to introduce two definitions really quickly, and then we'll move on to the multiplicative identity of the multiplicative identity matrix. So we have symmetric matrices. Symmetric matrices are those square matrices. So A needs to be a square, and we'll say n by n matrix. We say A is symmetric if A equals A transpose. So if you had something like, let's look at a quick example. Let's let A be like 1, 2, 1, 3, 5, 7, 3, 5, 7, like this. Well, if you were to compute a transpose and you were to swap rows for columns, well, what would you get? You would get 1, 3, 5. The first row of A becomes the first column of A transpose, second row, and third row, right? And so here you can see A transpose is the same as A. We call this a symmetric matrix. And the reason for the phrasing symmetric comes because there exists a symmetry now about this diagonal, right? If you flip over this diagonal, your matrix is the same. We also have skew symmetric. So A is skew. Again, let me emphasize here. Let me take the time to emphasize that A is a square matrix, right? Because we could never have these relationships. We could never have this criteria for a non-square matrix, right? Because the second you have a different number of rows and columns, well, then when you flip those, that's inherently a different matrix. So symmetry and skew symmetry for matrices is always going to be for square matrices only. So this is a square n by n matrix again. And then we'll say A is skew symmetric if, and what we have is now that A is negative, it's transpose. So we could take the same example and just flip some signs. So A could be 1, 2, 1, and then 3, 5, 7. But now let's say we have -3, -5, -7. Well, then A transpose, you swap rows for columns, you're going to get 1, -3, -5, 3, 2, -7, and then 5, 7, 1. Right, and you can see here, if you were to multiply the matrix A by -1, you would get exactly A transpose here, right? So this is an example of a matrix that's skew symmetric. Okay, then I now want to talk about the multiplicative identity. These are, and we'll simply just refer to them as the identity matrix, and these are for square matrices. So let's look at the n by n identity matrix. This is I sub n, and that's how we'll denote this as I sub n for the identity, and it's ones along the diagonal and zeros everywhere else. So something like this, where this is n columns and n rows. Okay, and so for example here, what's a 1 by 1 identity matrix? Well, that's just 1, right? Because it's ones along the diagonal, zeros everywhere else. The 2 by 2 identity matrix would be 1, 0, 0, 1. I3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And so this idea kind of generalizes, and what we can write this as, this identity matrix, is the I sub n identity matrix can be described as delta ij, like the entries are delta ij, where delta ij is a special function. It's called the Kronecker delta symbol. And it's the following function: delta ij equals 1 if I equals j, and 0 if I does not equal j. So maybe you've seen this before. If you haven't, that's fine. Really what this is Kronecker delta symbol, is it's keeping track of when the indices are the same, right? And so if the indices are the same, we get a 1. If they're different, you get a 0, right? And so you can see along the diagonal would be the only place where the indices I and j are the same. And so this would exactly give us the identity matrix. I want to state a quick lemma here. We have a lemma that says if A is an M by N matrix, then if we multiply A by the M by M identity matrix on the left, then we'll just get back A. And then if we multiply A on the right by the N by N identity matrix, we'll also just get back A, right? And this makes sense because for matrix multiplication, we know the dimensions of the inside, or the inside dimensions, need to agree. So for the M dimensional identity matrix, we have M by M, and then for A, we have M by N. And so here we're going to get an M by N matrix. That makes sense. And then for A, we have M by N, and the identity matrix here is N by N. And here again, we're going to get an M by N matrix. And you could go through and see that what you'll get back really is just A. Let's do some examples to kind of verify. This won't prove the lemma, but it will verify the lemma, right? So let's look at A being the matrix 2, 1, 5, 4, 9, 7. This is a 2 by 3 matrix, right? So if we have 2, 1, 5, 4, 9, 7, and we want to get A back by multiplying on the left, well, then we're going to multiply by a 2 by 2 matrix, right? We'll have the 2 by 2 identity matrix on the left. And now if we do matrix multiplication, remember we take the first row or the first column of A, and then we kind of write it up here. And for the first entry, we'd have 2 times 1 plus 4 times 0, so it'd be 2. And then we go to the next column, right? And we do the same thing. So then we'd have 1, 5. And then for the second row of the product, we would have 2 times 0 plus 4 times 1, 1 times 0 plus 9 times 1, 5 times 0 plus 7 times 1. And you can see we got A back here. Now, what about if we multiply by an identity matrix on the right-hand side? Well, that will need to be a 3 by 3. So we have the identity matrix when n is 3. And what are we going to get? Well, now we take the first column of I3, and then we go through the similar process, right? So we're going to have 2 times 1 plus 1 times 0 plus 5 times 0. And then you can go through the multiplication again. Like here, we would go to the next row. And then get 4, 9, 7 again. And this would be an example of, and this is why we call it the multiplicative identity, right? Because you multiply a matrix by this I sub n or I sub m, and you get the same thing, right? It's an identification. You get the same matrix that you started with before the product. Okay. Now, I think what I want to do here is I want to break the video here. And then what we'll do is we will look at the inverse of a matrix. In the next video, we will be primarily concerned with finding out what the inverse of a matrix is and how to calculate it. So.